Okay, we're going. Okay, so last time we talked about change of variables, and we did several examples. Keep in mind the big point to change of variables is that if your domain is an image, then you can pull back through the change of variables function and get a new integral with a new domain. And of course, integrals are, ugly sometimes, and having a new domain, hopefully an easier domain, will make life easier. Okay, so one of the big tricks to... question, yes?
Would, the domain pull it back to, would that, picture, be called, the pre-image?
Yeah, that's right. It's that'd be a reasonable use of the term pre-image. Yeah, absolutely. I also I find myself typically calling it the pullback domain just to emphasize that there is a pulling back process. But yeah, totally. Okay, so what we never really got around to understanding was where did that stretching factor formula come from, right? I just kind of cited it, and the justification I gave for why we wouldn't there and then justify the formula for it is that there was a lot going on, and there's a lot to keep track of, and it's confusing enough as it is, and I didn't really want to get, what I'm going to say, distracted. I wanted to get some wins under our belt, right? Let's see some examples of this in action, and then later we'll come back and let's justify where this stretching factor formula comes from. Okay, so remember the big idea is that if you have a little piece of area in your, you might call it the pullback domain, you might call it the first domain, however you want to say it. Little piece of area. The idea is that the change of variables function pushes that forward and kind of distorts it in various ways, right? To make its image. The big idea, of course, these are not the same size, right? This image on the right is being as it is distorted. Well, its area is going to be some factor times the initial area, and we need to know what that factor is. So I'm going to compute that by I'm going to start off by computing that area in the first place and see what we get. And it's going to turn out, you can see this coming. It's going to turn out as being a multiple of this initial little piece of area. And so that factor, that multiplicative factor, and of course you can see because the calculation's in front of us, you can see it is what we expect it to be. But being as that this is what you multiply by the green to get the blue, that's why we justify this as the stretching factor. Okay, so let's compute this area. How do we compute that area? It is a parallelogram. We have an existing formula for computing an area of a parallelogram. It's the absolute value of the determinant of, and again, this is just a chapter 1 formula, Math 218 formula. The vector defining one edge is the first column, and then the vector defining the other edge is the second column. All right, so that's ancient history, Math 218, chapter 1 in this course. Okay, so that leaves us then with the question, all right, well, how do I find these? Let's start with the first one. How do I find this vector? I claim that it's this thing. How do I justify that it is this thing? Well, think of this vector not as part of a parallelogram, but think of it as representing an output change in the value of the g function. G was here and then became there. Specifically, it's the amount that the g function changes as I move like this in the domain. And said differently, given this input change, we want to know what is the corresponding output change. And we have a thing for that. That's what derivatives do, right? The derivative matrix in particular. The derivative matrix is what you do to the input change, that I have in orange, to get the output change that I have in purple. So immediate sort of use of the derivative matrix. Well, that brings up the question, how do I know what this orange vector is? Right? So, well, this one you can kind of look at the picture. I mean, by assumption, I've got a little sub-rectangle here. This vector, I know its direction. I know its magnitude. It's pointing in the E1 direction because, well, look at it. Right? And its magnitude is du because this is a little piece of area of width du and height dv. So the width is the magnitude of this vector. The direction is E1, so E1 du. So, knowing this vector tells me by the derivative matrix that vector, which gives me that first column. Is everybody on board with that? All right, so ditto for the second one. Of course, now the second vector, the second column here, that's going to come from looking at the vertical, there, E2 dv. Analogous reasoning. And what do I do to E2 dv? Well, I multiply by the derivative matrix again. Multiplying by the derivative matrix gives me then that vector, which I lost track of my colors, is the second column. Okay. All right, and it's almost all over at this point. We've done most of the work in this argument. A couple of little things that have to be done yet. I'm going to point out that this du right there, that is a scalar factor, common scalar factor in this entire first column. Nice property of determinants. Common factors in columns factor out of determinants. Hope everybody remembers their determinant, algebra of determinants from Math 218. Likewise, that dv, common factor in a column, second column. Common factors in a column factor out. Okay, and that leaves us needing to understand just this matrix. Right, we're almost there. Right, we see that the area that I'm looking for, right, is a certain absolute value of a determinant times the area that I started with. I just now need to understand what is this matrix whose determinant's absolute value is that factor. How can I understand this green matrix? Okay. This also is a linear algebra thing. Let's look at this, specifically the first column here. What can I say about that first column? I've got a matrix times E1. Flashbacks to linear algebra. What happens to a matrix when you multiply by a standard basis vector? You get a corresponding column, right? So this thing here that I have in yellow, first column of the DG matrix. All right, let me say that a little bit differently. The first column of the matrix I'm trying to understand is the first column of DG. And likewise, the second column of this matrix I'm trying to understand is, the second column of DG. So this matrix I'm trying to understand has the same first column as DG. It has the same second column as DG. It's DG. That makes sense to everybody? It's a slick little move there. So all of this is DG. And we win. This recovers what we wanted, that the stretching factor, the thing that you multiply by the input area to get the output area, that is the formula that we previously claimed. Okay. Alrighty. So, all right. So, what about 3 dimensions? Right. Every example we've done so far, the theorem that we stated previously, everything we've done has been two-dimensional change of variables. So, what if you have a 3-dimensional circumstance? So, for example, maybe I have this horrifying domain here. What a nightmare that would be as a domain for an integral. Right? And let's just take a moment for humor value and think about, how would I slice this up? Would I do Y slicing or would I do X slicing? You're going to hit so many corners and you're going to sideswipe faces, and it's unthinkable. Right? Absolutely unthinkable to deal with that directly as a domain. But if I can view it as being the image of a simpler domain, such as this nice, convenient little box, right? Then the idea is let's copy all the ideas from 2-dimensional change of variables. Let's plan, fingers crossed, hopefully, to pull back through the change of variables function. Everything that's over here in my initial integral, that's in terms of x's, y's, and z's, let's plug in and rewrite it all in terms of u's, v's, and w's. And a lot of this is exactly the same. G gives x, y, and z as functions of u, v, and w, and so x, y, z is literally g of u, v, w. That's the plugging in part. Right? There's little pieces of volume, not area, but volume now over here on the right that I'm going to need to rewrite in terms of u, v's, and w. Again, I'm going to view them as being stretched out. Results of stretching out little boxes instead of sub-rectangles. Right? And the little sub-boxes that I would have over here, du, dv, dw. There is the question then of what the stretching factor is. I claim that the stretching factor is, again, that's seemingly the same formula. It looks like exactly the same formula, the determinant of the derivative matrix. Absolute value. Don't forget the absolute value. How do I know that it's this formula? I'm going to leave as an exercise for y'all. This is, I think, a really good exercise. We just talked through where this formula comes from in 2 dimensions. You can do a morally equivalent argument in 3 dimensions. Instead of having a little sub-rectangle, you're going to have a sub-box. You're going to have a 3-dimensional version of this. You push it forward, you'll have a 3-dimensional version of this parallelogram. You'll have a parallelepiped. Right? Question?
I guess I'm confused about where do you start when you start with these problems? Do you start with the square or do you start with the one that you don't?
You usually start with that the question has asked you to compute an integral on a domain, some weird domain. And keep in mind, this is just a small part of our weird domain, right? But you usually start with an integral on the ugly domain, and then the idea is you pull back, and that's what's counterintuitive, right? Because the points go that way, but expressions go the opposite way. That's because of plugging in. That's how plugging in works, right? You usually start off being given one of these, and you have to figure out how to view it as being an image of something nicer.
Okay.
Yeah. Yep. All right. So, you're going to take a 3-dimensional one of these, and it's going to have a 3-dimensional equivalent of these, which is still going to be determined by its edges. It's just that there's going to be there's going to be kind of a third edge, right, making it 3-dimensional. Those are still derivative matrix applied to these edges. It's still going to be a determinant. It's a 3x3 determinant. Everything kind of falls through in very, very analogous ways. So, your ability to make sense out of, to justify this being the formula for the 3-dimensional stretching factor is a nice little test of how much you understand this argument about the 2-dimensional stretching factor. And again, as you go through the argument, feel free to rely heavily on what we have here in sort of the 2-dimensional case. Okay, as always, when I give y'all, recommended, exercises, you're very welcome and encouraged to come to office hours and ask me about it. I'd be very happy to help you with it if you get stuck. And of course, you have other resources, help room, porter's office hours, friends, what have you. But feel free to come to my office hours for questions. Real quick, a notational thing. This determinant, again, we have this kind of, sloppy but convenient alternative notation to represent this determinant. And notice, of course, there's 3 outputs and 3 inputs. After all, this derivative matrix is 3x3 now. Okay, so I'm going to show you an example. In order to do this next example, I do need there's a quick little aside theorem that I need to talk about. I claim, in fact, we've already seen an example of this. If you have a linear transformation defined by a matrix, then the derivative of that linear transformation, the derivative is, believe it or not, the same matrix. This is another, one that's easy to check. But feel free to restrict yourself to just, 3x3 is plenty. And you can just write down a matrix, A, B, C, D, E, F, G, H, I, right? Just make up an arbitrary matrix That defines a linear transformation. Get your formula. Compute the derivative matrix, various partials, right? Assemble that matrix, and sure enough, it's going to be A, B, C, D, E, F, G, H, I. Exact same matrix. Let me show you where we've already seen an example of this. We didn't talk about it at the time, but y'all remember this example here. And I defined this rotation, right, as a linear transformation. And we rewrote it for the specifics at hand as that, right? So this is our rotation linear transformation in this exact case. And then I computed the derivative matrix, and sure enough, the derivative matrix, you'll notice, same matrix. Again, you probably didn't notice at the time. We were busy doing other things, but not terribly surprising. Okay. Alrighty, so that noted, here's the question. Here's the three-dimensional change of variables question. Want to compute an integral on a certain domain. Our domain is a parallelepiped, which, by the way, would be a nasty, nasty domain. If we were going to do this the old-fashioned way, if we were going to slice this up, sort of, dx, dy, dz, or what have you, those kinds of slices, horrible. Corners everywhere, right? There'd be tons and tons of fairly hard to draw pieces that I would have to break this up into, right? It's you really, really don't want to do this the old-fashioned way, right? Everybody happy? Okay, so how am I going to compute that? How am I going to pull that back? How am I going to view this undesirable domain as being an image? Keep in mind, that's your first step, right? If you want to do a change of variables, you need your ugly domain to be the image of a nicer domain, and then you're in business. Okay, here's the clever observation. I wish I thought of this. I didn't. Somebody showed me, and I'm showing you, right? But clever move. You should definitely put this in your little toolbox of tricks that you might be able to make use of. You never know when. The vectors that define the parallelepiped, those vectors, make them the columns, as you see I did here. Make those the columns of a matrix. That matrix defines a linear transformation. That linear transformation, and I'm going to justify this in a minute, but that linear transformation applied to the unit cube will result in the parallelepiped that you want. A really slick little move, really nice trick. The defining vectors, right, that you're given, make that a matrix. That defines a linear transformation, and that turns the unit cube into your parallelepiped in question. All right, now I got to explain why this is true. I can't just assert it. Got to show you where this comes from. So here's the argument. Let's think about this E1 vector right here. Right? What happens if I take the E1 vector and put it through this linear transformation? I've defined a linear got a matrix. Matrix is a linear transformation. What happens if I put E1 through it? Well, if I put E1 through it, right? I'm going to be multiplying, you'll notice, that matrix times E1. I've lost track of my colors again. This matrix, A, that matrix times E1. What happens when you multiply a matrix times a standard basis vector? You get the corresponding column, right? So this product, matrix times E1, gives me that corresponding column, and that is, by construction, that first vector defining the parallelepiped. So it just works, right? And you can kind of see, once you see it in action, you can see that, I rigged it up to where this was going to do what I wanted it to do. And likewise, analogously, the image of E2 is going to be the second vector, and the image of E3 is going to be that third vector. And so follows the image of the unit cube is my parallelepiped. Is everybody happy? That's most of the work in this example. Again, the big challenge is finding a way to view your undesirable domain as an image, and then we can just cite the change of variables. We pull back. Everywhere I see, well, let's see, I'll do it like this. My volume on the right is stretching factor times volume on the left. There's my stretching factor. Going to have to compute the derivative matrix of your linear transformation. Oh, wait. Our linear transformation is defined by a matrix. The derivative matrix is the same matrix. So that's kind of neat convenience, right? This is, I'm citing our result from up here. The derivative matrix, same matrix. Okay. So I've got my stretching factor. I guess there's one last little detail. Technically, the integral that I was asked to compute, you see, is an integral of z. Got to figure out what z is. Well, don't forget, z is the third output from our linear transformation. I can see the outputs of my linear transformation. Right, there's my linear transformation. The third output is the third. Let's see here. If I were to multiply by u v w here, like so, right? Then multiplying a times u, there it is. What's the third output? The third output is going to be the third row dot uvw. And that's that. How we doing? Yep.
If you change the orders of columns, but kept the handedness of like the pair.
Yeah, it doesn't make any difference. Yeah, it's a great question. That's part of the reason why we have to take the absolute value when we do the stretching factor, is that we never really know if we have in some sense, an inversion or not, right? If someone were to give you these three vectors, these three defining vectors, defining our parallelepiped, they give you those in a different order, yeah, sure, then you'd have a slightly different matrix, it'd be a sort of a shuffling of the columns, and you would ultimately get the same answer. Yep.
Even if the handedness was like switched.
Yeah, because if you switch the handedness, right, effectively what you're doing is you're just switching columns. Every time you switch columns, you get a minus sign on your determinant, and that minus sign disappears in the absolute values. Yeah, so it really doesn't matter. It's a great question. Yeah. Does that all make sense? Yeah. Okay. Alrighty. So, nice example there. Okay, we're going to move on now and talk about the sort of the second, I'm going to call it the second half. Even that's a little bit of an understatement. I've already commented how this section is massive. It's massive, right? I don't know that we'll finish it even Friday. We'll see. Hopefully, oh gosh. It's just huge. So we've spent a bunch of time talking about change of variables. It's a big topic, a lot of ideas. Now we're going to talk about a very closely related idea called integrals in a coordinate system. We're not going to finish this today. Right? This is still in the same section. And then there's some other stuff that really naturally fits in with this same section, but that's not in the book. And so there's some supplemental material on symmetry theorems that we're going to do after that. So we'll see how long this takes us, but it's all good stuff. The big idea, the first big idea is that coordinate systems, such as polar coordinates, and here's what defines our polar coordinate system right here, right? These formulas for x and y as functions of r and theta. If you think about it, that gives a domain, the r theta plane, a target, the xy plane, and in fact, what I have therefore is a function from this two-dimensional world to that two-dimensional world, I can choose to view this as a change of variables function. Now, the question comes up, is this going to be useful? Right? Well, we don't even have a domain yet. How do I know that this is going to be useful for, what kind of domains is it going to be useful for? We'll flesh that out later. Right? But I claim that it's going to be useful for lots of domains. And we can view this as a change of variables function. We're going to compute the stretching factor now so that we never have to do it again. And then we can plug in. So easy calculation. Again, here's our formula. And you can compute the various partials. Arrange the derivative matrix and take the determinant. And there's some details there. You see I've left those out here. This is another, I'm going to say, exercise for y'all to do on your own. Everyone should do this once in your lives. I did mine. And it's not hard. It's very straightforward. It'll take you about a minute, maybe, right? There's a couple of partials, a little determinant. Don't forget the Pythagorean identity. It's going to come up, and out comes your answer that your Jacobian determinant is just R. So that means that your stretching factor, which of course don't forget the stretching factor is the absolute value of the Jacobian determinant. Your stretching factor is absolute value of R. Everybody with me? Again, details to be filled in by y'all later. Okay, bad news though. It's got absolute values in it. We don't like absolute values. We would like to, if possible, find a way to get rid of those absolute values. And here's how we're going to do it. We now have a pretty strong motivation because we don't want to have to deal with absolute values every time we do one of these kind of questions. Pretty strong motivation to require R to be positive. So that's all we got to do. All we have to do is just promise that we will stay on that side of the line, right? Only choose positive values of R. And if you do that, now you're taking the absolute value of something that is never negative. In which case, that absolute value is just the value itself. So that's the deal. Now y'all will recall that I resisted back in chapter 1. I resisted requiring R to be positive. After all, there's nothing about these equations here, not a thing about these equations here that particularly motivates tying our hands and not allowing ourselves to choose negative values of R. Who knows? It might be useful at some point, right? There's no reason not to, so just leave it be, right? Now we have that motivation. We're going to require R to be positive because it really helps us in our formula for our stretching factor. Okay. Alrighty. We do the same thing in cylindrical coordinates. Same deal. Here's the formulas. It's a function from R3 to R3. You can view this as a change of variables function. You can compute the Jacobian determinant. Again, details for y'all to fill in. It's not that bad. It's, there's a few extra details. Not much. In fact, you're going to find when you do this calculation, it's really similar to the polar coordinates one. Really similar. But a little different. So make sure to go ahead and go through and do that. The answer is R. So again, don't forget stretching factors are always the absolute value of that Jacobian determinant. So here we are again. We have another absolute value, and thus we are again motivated to want to require that, if we were to just require going forward that R is always positive, non-negative, then absolute value goes away. So analogous deal. All right, ditto spherical coordinates. A little bit of a twist at the end, but spherical coordinates, basically the same deal. We have formulas. It's a function. I can compute the Jacobian determinant. By we, I mean you. This one's more non-trivial. Now again, everyone should do this once in their lives, right? And I encourage you to take a crack at it. This one actually is a little tedious. It'll probably take you 5 or 10 minutes because it gets a little out of hand. The formulas are a little ugly. There's more trig. So a little uglier. But what you're going to find when you do this is that the Pythagorean identities, again, kick in big time. And there's at least 3 instances of the Pythagorean identity taking what otherwise would be a nasty formula and simplifying it dramatically. And what happens is that. So there's your Jacobian determinant. Again, we have the same sort of an issue. Stretching factors are absolute values. So this is where things get a little different. I'd like for the thing I'm taking the absolute value of, I'd like to know that it's always positive. What can I require that would make this thing on the inside always positive? And there's a temptation to think, okay, well, I'm just going to kind of rip off what we did with polar coordinates. Polar coordinates are needed to be non-negative. I don't know. How about rho? Let's make rho non-negative. But notice it's got nothing to do. It doesn't help at all. You make a promise that rho is non-negative, and okay, but it was going to be squared anyway. It really doesn't help you. Right? What you need to be worried about, if you want this thing on the inside to be non-negative, it's not the rho squared that's the problem. It's the sine phi that's the problem. That's what you need to make a promise to in order to get this to where it's not ever going to be negative. So how do you make sine phi never negative? You choose these values for phi. So there's no restriction on rho in spherical coordinates. The restriction is you have to choose phi to be between 0 and pi. Okay. Everybody with me? Good news. Those are everybody's favorite values of phi anyway, right? Phi equals 0, straight up. Pi is straight down. These are sort of the natural and obvious, best, you might say, values of phi. So if you promise to do what you were going to do anyway, right, then you get to throw away the absolute values that you didn't want to deal with anyway. It's win-win. Okay. All right, so let's see one in action. Here is a question. We want to compute this integral right here. We've got a domain. The domain is a quarter disk, and let's take a moment to speculate on how hard this integral might or might not be. The domain's not that bad. We don't have any corner issues. But the thing is, when you solve for y as a function of x or x as a function of y on that top right curve there, you're going to have square roots. So whichever way you slice, you're going to have square roots on your inner bounds. Which means you're going to have square roots in your outer integrand, and when there's square roots in your integrand, the integral's hard. So brute force, I mean, I'm not saying you can't do it. I'm saying it's going to be I don't even know, integration by parts, trig substitutions maybe. I don't know. You got to write it down and see what happens, but it's going to be annoying. All right. That makes sense to everybody? Okay. All right. I claim that quarter disk is the image by the polar coordinates function of this rectangle. And I got to justify that for you, but you can see why this would be good news, because doing an integral on this rectangle, no problem. It's a rectangle, everybody's favorite domain. Right? So now, how do I know that this is as I claim? Well, you can kind of look at one edge at a time, and let's start over here. Let's look at that edge of our given domain. This is, theta equals 0. R goes from 0 to 1. And over here, theta equals 0, r goes from 0 to 1. That's what it looks like in the r theta plane. Everybody good? And then you can kind of make your way through the rest of this. Here, that edge is r equals 1. Theta goes from 0 to pi over 2. That's that. And let's see here. This edge there is, okay, theta is pi over 2, r goes from 0 to 1. Okay, well that's that. right? And then I'll point out that sort of the missing edge over here, if you think about it, this entire edge here is where r is equal to 0. That entire edge is just this point there. So the stuff that's on the inside of this rectangle goes to the stuff that's on the inside of that quarter disc, and we win. What do you think? Everybody happy? Okay. All right, and then it's all over but the shouting. Let's see here. You got to pull back, and x squared plus y squared in the pullback is r squared. Convenient. We've got to deal with the stretching factor, and so dx dy that we would have had for this domain turns into, don't forget your stretching factor, r times dr d theta over here in the pullback domain. So r dr d theta. And we have now taken our integral that initially was on this undesirable domain, and we have turned it into an integral now on this much more desirable domain, which you can see how desirable it is. Look, bounds are right there, right? R and theta, constant bounds because it's a rectangle. What do you think? Everybody happy? Yeah. Mm-hmm.
Will we ever have to change the order of integration?
You mean like these?
Yeah.
I'm going to say never, but there is a very strong tendency, and I'm going to make a comment about this further later down, that it's just practically always best to do this order, dr d theta. Yeah, practically always. Oh, good question. Okay. All right, now we're not quite done. You do have to actually crank out this integral, but everything's looking good. The only little twist that I want to point out, some students forget about the r. They might even put the r in there, but then when it gets to time to doing the antiderivatives, they, for some reason, will just take the antiderivative of r squared, because that was the integrand of the other integral. Right? But don't forget, your stretching factor counts. That's why it's there. So your integrand for this new integral is r cubed. And so the antiderivative is 1/4 r to the 4th. Right? So don't forget to merge your stretching factor in with the rest of your integrand. Again, that's why it's there. Okay. Alrighty. So what we have done here is we have used a coordinate system to allow us to do a change of variables. Now, I'm going to give you a different point of view on this that actually is going to streamline it very nicely and turn this process into a even more efficient process that I'm going to call an integral in polar coordinates, which is not really quite exactly what this is. And the observation is to point out that when I do my slices, when I take my theta slices, and going back up here to my new domain, I've got to take theta slices. Here's what theta slices look like, right? Constant values of theta. And then once I've done my theta slicing, I've got to take an arbitrary theta slice, and I've got to see, well, where does r start and where does r end? Right? I've got to, in some sense, slice my slice. The thing is, I can see all of that in the xy plane. So here's theta slices. One at a time. What does this theta slice look like? That's theta equals 0. Okay, it's that. What is this next theta slice? That's theta equals some slightly larger value. Okay. All of these theta slices are just slightly increasing values of theta, and I can see exactly what they look like over here in the xy plane. They're just rays coming out of the origin. So, yeah, you do have to theta slice your pullback, but you can see it happening without pulling back. So that's just an observation. Likewise with R. If you're doing R slicing, R slices look like this. They're, again, constant values of R, slicing perpendicular to the R axis. Well, constant values of R just kind of look like this in the XY plane. So I can see this happening in the XY plane as well. So, in fact, keep in mind, most of the time what I need to do is do my theta slicing and then take my theta slice and do the R slice of my theta slice. So again, here's my theta slice and the R slicing of it. Just like that. So what we're going to do, instead of pulling back over into this new world, this R theta plane world, and drawing the picture of the pullback domain in this new world, and then slicing it up business as usual, we're just going to leave it where it was and imagine what we would have done over here by looking instead at the pictures of what that looks like in the XY plane. So theta slices are like this. And then given a theta slice, R slices, just chop that up. Let me show you an example. So here's the exact same example that we did previously. Right? Exact same one. First quadrant portion of the unit disk. Previously, we drew that there is a change of variables function. We drew the pullback domain, and we went to some trouble to explain how we knew what this pullback domain is. We're not going to do any of that this time. So pretend like that isn't even there. Right? And I'm just going to say, all right, well, on this domain, there's my first theta slice. That first theta slice happens when theta is equal to 0. So my starting value of theta is 0. And then my theta slices kind of look like this as I go along. These are all different theta slices. And then my last theta slice is there, which is where theta is pi over 2. And that's my upper bound for theta, pi over 2. So I don't need the pullback domain. Everything that I need from it, I can witness right here in this picture. Theta goes from 0 pi over 2. Boom. Does that make sense? Okay. All right. Then likewise, for a given value of theta, let's pick some arbitrary value of theta, somewhere between 0 and pi over 2. What are we going to do with that? Well, okay, again, you could think of that as being a theta slice over here in the pullback domain, and we could try to keep track of, well, where does R start and then where does R end? But you can see that right here. It starts right there where R is equal to 0. And then it moves along until you get to the end. You get to the end point there, which is where R equals 1 because it's a unit disk. And so R, 0 to 1. So again, you could see it here, but you'd have to draw a whole new picture. Don't bother. Everything you need to see about it is already right here in the picture you started with. Okay, how do we feel about all that? Everybody happy with this? This is what we call doing an integral in polar coordinates. Technically, yeah, it's a change of variables. Fine, good to know, and don't forget about that. That is important. But in practice, day in and day out, doing the integral in polar coordinates just means reconceive of what slicing looks like, appropriate to the polar coordinates, and don't forget your stretching factor. There you go. All right, let's see another example. Okay, the entire unit disk. Various different ways that you could think about this. I'm going to start, just because it's the most convenient, by saying, well, let's start looking at this slice where theta is equal to 0. And then let's kind of keep slicing. So here's my various different theta slices. Theta keeps getting bigger, you'll notice, as I go around. And then when I get to where I'm done, I'm kind of back to where I started, kind of, but not. I'm pointing in the same direction in the XY plane, but don't forget, we went all the way around. Theta literally increased all the way until I get, let's see, again, back in the same direction, but that's a full turn. That means theta increased up to 2 pi. What do you think? Everybody happy? Okay. All right. And then, of course, you pick an arbitrary theta slice. For that theta slice, You can look and see what R does, and this is a unit disk, and so R starts at 0, and R ends at at the edge of the unit disk where R is 1. So R goes from 0 to 1. Everybody good with that? And notice how easy it is to punch up this integral. And by the way, let's take a moment to think of this would be a real pain in rectangular coordinates. I mean, there's a square root in my integrand already. There's going to be more square roots that come from the fact that whether you solve for x or y, either one, you're going to have square roots in those bounds too. This is a pretty unappetizing looking integral here, right? In polar coordinates, we have a polynomial, no square roots, and we have constant bounds, and it's just a really easy calculation. Okay. All right. So I have some general advice. Let's see. And by the way, is this? Okay. General advice for when you do integrals in polar coordinates. Somebody asked this already, but practically always you want the dr on the inside. It's very, very rare for the other order to be better. It's actually fairly rare for it to be as good. But there's no point in doing it in the other order. So always do this order. As far as Math 219 is concerned, always do it in this order. You'll be fine. Okay. Here's the other thing. I strongly advise that you always, when you're writing down your integral in polar coordinates, write that r in there at the same time that you write the dr d theta. Because if you don't, it's really easy to forget. Let's see here. There you go. Forgetting is very easy. The way it goes down is you write dr d theta in recognition that you're about to do some slicing, and then you go off and you look at your picture and you're thinking about slices and slices of slices and bounds and such, and then you just forget to go back and insert the stretching factor. Surprisingly easy to forget. If you write these down all together, then it's basically impossible to forget. So I think that really helps a lot. I hope you'll do that. I mean, there's, again, this temptation to say, I'm going to write this part down now, and I promise I won't forget, and I'll write this part down later. But it's so easy to write it down at the same time. So, again, I think it's a really good idea. And then the slicing process is just like all of our other slicing processes. You just have to identify the relevant points, which are on which curves, which have certain equations, and then solve for the bounds that you want. Let's see, how are we doing on time here? We are mysteriously ahead of the other section. Weird. Okay, I tell you what, we don't really have time to do the next example. I've gone over enough times that I owe you some minutes, so we'll end 2 minutes early today. See y'all later. Stick around if I didn't mark you